Good afternoon. Welcome to this symposium on advances in additive manufacturing, also known as 3D printing. This symposium is supported and endorsed by the Italian Consulate in Philadelphia and organized by Philitalia International, a prestigious Italian-American non-profit organization founded 34 years ago in Philadelphia to promote and preserve the Italian culture, heritage, and language throughout the world. We are broadcasting live, but the recorded version of this event will be posted on YouTube in a few days. My name is Antonio Paesano and I will be the host of this symposium. A coloro che ci seguono dall'Italia, buon pomeriggio. Benvenuti a questo simposio sui progressi in 3D printing, patrocinato dal Consolato Italiano in Filadelfia e organizzato da Philitalia International, una prestigiosa organizzazione senza scopo di lucro fondata 34 anni fa a Filadelfia per promuovere e conservare nel mondo la cultura, le tradizioni e la lingua italiana. Stiamo trasmettendo in diretta e la versione registrata di questo evento sarà caricata su YouTube tra pochi giorni. Mi chiamo Antonio Paesano e sarò il moderatore di questo simposio. Before leaving the floor to our esteemed speakers, we have some esteemed guests who would like to welcome the audience and say a few words. I'm starting with the Honorable Pier Attilio Forlano, Consul General of Italy in Philadelphia. Mr. Forlano, it is a privilege having you today. I pass you the microphone.
Thank you very much, Antonio, and thanks to Philitalia and to all our speakers. You know, Philitalia is doing an amazing job since 34 years ago, like you were saying. It's one of the column, one of the beacon of the associations of Italians in Philadelphia. And it's just thanks to Philitalia that we have a beautiful museum of immigration in South Philadelphia, which speaks about all the endeavors of the Italians that firstly immigrated here in the East Coast. So thank you very much for Philitalia. Keep the good job going and kudos to what you are doing so well. So speaking about additive manufacturing, it makes me think about a little bit to the word added value, which is what the Italians strive to always bring to their work. So I will have two observations for you very quick. The first is rather intuitive. We are, like you know, the second industrial country in Europe. There are no natural reserves in Italy, no whatsoever natural reserve, no oil or very little oil, a little bit of iron, that's it. So since the onstart of our industrialization, what the main characteristic and the feature of our added value was culture. We were able to apply to the Industrial Revolution a lot of cultural intakes and inputs. So if you want to delve into this beautiful matter, I prompt you to have a go at the page italianinnovators.com. Also, please keep yourself abreast of all the beautiful events that the consulate is organizing in Philadelphia. And for that, you can Google ciaophiladelphia.com, which is our website where we list all the beautiful scientific, artistic, cultural, linguistic events that we have in the year, ciaophiladelphia.com. So the second, more counterintuitive observation that I wanted to say is that possibly this value added, this added value to the industry is also due to the fact that Italians have the highest rate of self-employed workers in Europe. which no one knows because possibly they think that we Italians always think about that, you know, an employment for life, a job for life, but many workers out there are self-employed, and it obliges them to adapt rapidly, to think dynamically. So I will now also apologize because since I will able to follow this webinar only partially due to my conflicting commitment today. And but again, I wish you good work of good commentaries. Antonio, you're doing a great job, and I pass the floor on to you back. Thank you very much.
Thank you, Mr. Consul, and thank you for your presence and your message, and very interesting statistics, which I confess I ignored. I had no idea. So, all right. So if Dr. Nestico is not here, we will move on to the speakers. And I have to say that it has been a privilege to have today's speakers. They are accomplished and qualified experts in their field and will share today valuable and advanced information about additive manufacturing. As a side note, two speakers, Mr. Belisario and Dr. Pugliese, happen to be of Italian descent, confirming that still today, Italian Americans play a significant role in the American society. There is a question and answer icon on your screen, question and answer. So the audience can post questions by clicking on that icon, Q&A icon, and using the chat option. And after each speaker has finished, I will read the questions to the speaker, and the speaker will answer the question. Okay, so now we switch to the speakers. I am in the awkward position of introducing myself as the first speaker. I work at Boeing in Philadelphia as additive manufacturing lead, and have been developing and applying new materials and technologies for more than 2 decades, which I documented in my publications, patents, and book chapters. I received my PhD in materials engineering from the University of Naples, Federico II in Italy. My presentation today describes only the most basic information on additive manufacturing. It is very short and serves as a brief introduction to the next speakers, who will provide more specific information about additive manufacturing and its applications and intellectual property. Next slide, please. So additive manufacturing, in very simple terms, is the process of making, also known as 3D printing. Printing is the process of to make objects layer by layer, starting from three-dimensional digital models that are three-dimensional computer models. And so additive manufacturing consists in basically adding material, whereas conventional manufacturing, such as casting, forging, machining, injection molding, etc., consists in removing material from a block or plate, or fabricating an entire part altogether. Additive manufacturing uses basically all engineering materials: plastics, metal, ceramics, and any combination of all the above. Next, please. Now, the typical steps to 3D print an object are shown here on the upper part of the slide. So first, step one, we draw a three-dimensional computer-generated model, also known as CAD model. CAD means computer-aided design. Step two, we convert the CAD model into a STL file. That is a file containing the coordinates of the points defining the geometry of the object. The STL file is important because it is read by the computer running the 3D printer. Step three, the STL file is converted in slices, making up the full geometry of the object to be printed. Each slice is printed as a layer. Step four, the 3D printer lays one layer at a time and stacks each layer on the layers previously laid. Step five, the printed object is removed from the printer and is finished by removing the support material, by sanding, by heating, etc., the part. Next slide, thank you. So I will show today only, so there are several types of additive manufacturing processes. Today I will show two of the three most important types: powder bed fusion and fused filament fabrication. Dr. Pugliese will describe another very popular type of additive manufacturing process. Now here I'm showing the fused filament fabrication process. In this type, the feedstock material is in form of filament and it is deposited layer by layer. There are two feedstock materials in this process. One that stays in the final object and the other one that is called support material. The support material is deposited below overhangs, inside cavities and holes to prevent overhangs, cavities, and holes from deforming, sagging, bending under their own weight due to the force of gravity. Next slide, please. Here are some examples of 3D printed parts using metal, a metal filament, basically, a metal filament. And you can see the lines, traces of the layer deposited one over the other, indicated by the white arrows. Next slide, please. This is one of the three most popular families of 3D printing processes, and it is called powder bed fusion because the feedstock is in form of powder. This process consists in spreading the powder one layer at a time, heating the layer up, and fusing the powder particles together using, in this case, the heat generated by a laser beam. In this picture, the powder is moved from its storage tank on the left to the platform on the right on which the object is printed. Next slide, please. The next slide shows an example of a part printed from plastic using powder bed fusion, and you can notice the details, the intricate details. So this part is made in one shot, in one run, and may require a little bit of finishing to touch up on on the whole, so some of the details, but it's I would say it's 95% or more done, completed. That's my last slide. Thank you for your attention. And let's see if there are questions. Actually, I should read myself the questions. Let me see. Okay, no, I see no questions. Benny, do you have questions? Okay.
Actually, I do have a question. I'm
Okay.
curious.
Thank you.
Like when they pull it out, like how does the powder, does it get like stuck inside? If there's any like crevices, how do they have to like shake off the final piece?
Yes, so you shake off first. You shake off the part from the rest of the powder. Then you may use some brushes. You have to remove the if it has been used, you remove the support material. So if we look at the previous slide, for instance, the plastic part, there were some cavities, some holes. Yes, so if we might have used support material here, meaning we might have filled the holes to make sure that they stayed circular, they stayed round, they didn't become oval. And so you have to remove the support material. In that case, you have to use some drill, or you can basically cut it out. Then with some plastic materials, they require to be so-called post-cured, which means you have to heat them up at some high temperature in order for them to achieve their highest value of strength and stiffness and hardness and impact resistance and so forth. So there may be some post-processing to do, but it's not always the case. It depends on the material.
Oh, okay.
So, yes.
So you're saying the laser gets it to a certain hardness initially, and then you shake off the pan.
I was thinking of another process which is called which is based on liquids, where you need to, in that case, you need to post cure the solid part after it has been printed. But with powders, you may require post curing, although it's not generally the case with the materials used for this type of process.
Thank you very much.
Yeah, you're welcome. Okay, so let's move on to the next speaker, which is Mr. Lucas Jansen. He is the CEO, very young CEO of CEAD, a Dutch company providing large-scale 3D printing solutions for thermoplastic composites to several markets worldwide, including ships, boats, automotive, and aerospace. In his role, Mr. Jansen, I hope it's Jansen, not Jansen. Look, yeah, Jansen.
Yeah.
Okay.
Jansen.
Yeah. So Mr. Jansen worked as an industrial design engineer for more than 10 years in the field of additive manufacturing for business to customer and business to business markets. Mr. Jansen, you have the floor.
Thank you for the very kind introduction, and I'm very happy and honored, to be honest, to be here and to present to you a little bit more about additive manufacturing and about everything that my company does on large scale, specifically on large scale additive manufacturing. Yeah, so let's get started. I'll pop up the presentation. Quickly have to go here, and if I'm not mistaken, then you can see the opening slide for the presentation.
Yep, that looks good.
Perfect. So in this presentation, I want to tell a little bit more about what 3D printing with plastics and 3D printing with composites is about. and especially what it is about on large scale, and for which markets this applies, and what kind of equipment is needed for this. And my company Seed, located in Delft in the Netherlands, works on this field, where we really specialize in large scale 3D printers, as I mentioned, and we do this with a lot of partners. And most important partners are German partners, but also a lot of Italian partners. So I think that's also very nice to see the big influence Italy has also on this market segment, where we collaborate with Comau, for example, who's a manufacturer of robots, and with Belotti, the manufacturer of CNC machines. And to start off the presentation, I want to introduce the team. As you can see, we have a very young team. We're still a small company. We're at the moment with 20 engineers working on the technology on a daily basis. And the company was started in 2014 in the Netherlands. And at the moment, we work with 2 different technologies, which I will introduce shortly. But first, to come a little bit back at what Antonio also presented about 3D printing, is that it's a process where parts are manufactured layer by layer, which really excels in parts that are complex in terms of the shape, parts that need to be manufactured in a short amount of time, and parts that are manufactured in very low quantities. So that's also a very important aspect. And there are some logos or some symbols on this slide which show the different processes for printing with plastics. In the top, you have the production methods where you have a resin, basically a liquid plastic that is being hardened by using light or lasers or other processes. And in the bottom part, there are other processes where either a powder, as Antonio also outlined, is being solidified, or the processes where molten plastics are stacked layer by layer. And for this presentation, and also for the presentation that, or for the process where Seed focuses on, I will dive deeper into the process where layers are melted and stacked on top of each other. And this next slide shows a little bit more in depth how that works. I'm not entirely sure if the audience is familiar with other plastic processing methods, but for example, injection molding or other extrusion-based processes use the same extruder, which basically is a screw that transports the plastic in a molten state all the way down to the very tip of the extruder. And in this case, by moving this extruder, or also often referred to as print head, around in a 3-dimensional space, you can build up these parts layer by layer. And what our technology and where large-scale 3D printing with these materials really excels is, on one hand, the production speed that it can reach. We have solutions available where 80 kilograms per hour can be reached. So 80 kilograms of a part can be built up in 1 hour. Of course, this depends on how big your machine is to eventually also make these big parts. But another aspect where this technology excels is that you can use a very broad range of different materials. You can use commodity materials such as polypropylene, or even very high-end materials such as PEEK, which are all acronyms for polymeric materials. And you can also, with this technology, add fibers. And imagine adding carbon fibers to plastics really brings out or increases the strength of the materials drastically. And on this next slide, you can really see the different, let's say the wide range of materials that you can work with. In the middle, you see the segment of commodity materials. So these are the materials that you see on a daily basis. PP, polypropylene. You can see this in bottle caps, for example, but it's also used for a lot of industrial applications, such as your car bumper. ABS is very known from Lego bricks, for example, but is also very commonly used in 3D printing. And PAT is a material that you know from the PAT bottles, for where Coca-Cola or other manufacturers put in their soda. But you can also use high-end materials such as PEEK, which is, for example, material that is being used in the oil and gas and the aerospace sector a lot for very high performance applications, where there's a very high thermal resistance, which basically means it can take up a lot of heat before it fills. And then all the way on the left, there's also another segment which is quite interesting, but is not used that much yet. But this is the segment of bio-based materials, where in this case the material is not made from crude oil or at least an oil derivative, but it's actually made from bio-based sources such as wood fibers, lactic acid, or even starch. And with these materials can also be printed, and this also in turn excels the applications for the in the market for these bio-based materials. So that's to give a sense of the broadness that the technology works with. Now, everything that I've covered is still very theoretical, so I want to go briefly through the systems we supply to give you a little bit better understanding of how big the machines are, and eventually end up or round up with what they can do and what kind of applications you can expect from this technology. We make a division between two different setups. On one hand, the robot-based machines, and on the other hand, the gantry-based machines. And basically, the robot-based machines is where you take a robot arm and you make this into a large-scale 3D printer, which in turn gives flexibility to the user. The gantry-based machines are really excelling in the aspects of speed, so they can produce faster. They can also make larger parts, and they can work on a higher precision. So, but I want to start off with the robot-based solutions. We call this the AM FlexBot, as it's a very flexible solution, where a typical machine looks like this. On the right-hand side, you see a picture of this robot. In this case, a Comau robot, an Italian robot. We only work with this brand, and this robot is being driven using a Siemens Cinemeric controller, a CNC controller, which makes this robot more accurate and makes it easier to use this robot in this environment. And then we supply all the auxiliary equipment, such as the print head, for example, and the print bed. So the two very important things to really make it into a 3D printer. And of course, we deliver this in with the safety caging and everything installed. So imagine that you're a company that works on aerospace components, then this would typically be something that you could set up to quickly produce parts. As I mentioned, the Comau robot, it will lift this extruder at the end of the robot, and this extruder is the system that eventually starts to melt the different thermoplastics, and the robot moves this extruder around so that it can build up layer by layer. Using all sorts of different materials, and also varying between an output of 12 kilograms per hour up to 80 kilograms per hour. And I mentioned that the robot is a flexible system, and that's partly because this robot can quite easily swap between different functionalities. So now in this movie, you can see that it's leaving the print head behind, and it's now swapping to a CNC machining head, which allows you to finish your product. Maybe you can already see it a bit in this video, but when printing, you always see layers stacked on top of each other, which does not give a completely smooth surface. And the CNC machining option can make for a smooth surface finish. So on the right-hand side of this slide, you can already see the Comau robot again using a CNC machining head to completely smoothen the surface, which is of course for visually aesthetic purposes, but also for reaching specific tolerances that one may need in demanding sectors such as the aerospace or maritime domain. And the robots, they can be placed on tracks. So on the right hand, you see the robot on a track, which drastically enlarges the build volume of the robot. If you look at these machines, not only the machine itself is important, but also the software that it will use. So here you can see the software running a simulation of how the robot will print a part. So you see the robot moving in the video, the print head being at an angle at 45 degrees, and you can see it depositing different layers on top of each other, which you can use to again check your geometry and to also predict how the end result is going to look. And this can then be integrated in a next step where you take this, where you swap your printing head for the CNC machining head, and you do an additional machining functionality to, as I mentioned, smooth up the surface. So those were the robot-based solutions. I see that I missed a slide here, but we also, as I mentioned, produce these gantry-based solutions, and we do that together with Bellotti. That's an Italian manufacturer of CNC machines. And by combining those two experiences, we're able to also make very large gantry-based solutions, which essentially have the same flexibility as the robot, but they simply offer higher accuracies and faster production speeds. And then you may ask, why is this technology interesting to the market? And that's why I want to cover some of the applications that this technology is being used for so far. And we actually divide this in 3 different categories. On one hand, we have molds and tooling. On the other hand, we have non-structural end parts, and we have structural end parts. And molds and tooling are essentially, tools that help you in production, or molds that are being used to manufacture an end product. But the technology can also be used to make end parts. And then in a lot of cases, these are non-structural. We'll cover some examples, or they are structural elements, which of course makes it more difficult, because it really needs to take up a lot of strains and stresses. It really needs to be a very strong product. But to start off with molds and tooling, as I mentioned, these are components that are being used in production to eventually make end-use parts. And there's one example that's being used a lot, which is tooling. They call this autoclave tooling, which is used, for example, to make carbon fiber parts. So imagine that you're making a Formula 1 sports car, or you're making carbon fiber parts for the aerospace industry. This process can be used to make these tools. And maybe I can go a little bit back in the movie, but you see the robot printing a tool. Of course, this is a speed up, and then the robot has swapped to the CNC machining head, and piece by piece, it starts to remove only the top surface of the piece to make a fully functional surface that can be used for laminating carbon fiber on top. For example, for a Formula 1 sports car. Actually, this, as you can see, is also a tool made for a Formula 1 sports car. So, to give you an idea. It does not necessarily need to be used for these very high-end, high-performance applications, because, for example, making tools and molds for concrete casting elements is also a possibility, especially when you have more complex shapes that need to be produced. So this is a tool that was manufactured using the technology where a concrete tile or element has been produced in. So that's another good example of molds and tooling. On the other hand, what if you can also produce the end-use parts? So skip the step of producing molds and tools altogether, and that's also possible, but it's of course a little bit more challenging, because You may also need to look at UV resistance of the materials, or fire resistance, or other elements that are specific to that. And a good example of making such a non-structural end-use part are air vents that are being used in buildings, where where it replaces traditional aluminum, for example. And in this case, the air vent is first printed, and then again swapping to the CNC machining head. It allows you to finish it up, adding the holes to the part to make it into a fully functional air vent. So that's one example of a non-structural end part. And another one is this hatch for a ship, where it's replacing an aluminum part. Traditionally, these are made from really big slabs of aluminum that are completely CNC machined. So there's a lot of material waste, but they are also very heavy. And using this technology, you can produce with one robot this complete ship hatch. This was for a German naval shipyard where they produce luxurious yachts. And this hatch was produced in one day using this robot, and it complies with all the standards. So these are nice examples of non-structural end parts, because they still need to be strong, but they are not structural. So if this hatch breaks, the ship will not sink, the ship will not break itself. But there are also structural end parts, and one of the examples that I wanted to share with you is a structural end part is a pedestrian bridge. This is a project that we do in the Netherlands, and there are a lot of pedestrian bridges to cross the waters in the Netherlands. And these are, of course, structural elements, because if this element breaks, if this material is not strong enough, actually people will get hurt. So it's very important, of course, to have your calculations right. That's also why this is a more a more, let's say, complicated application. But at the same time, it's also very nice to see that the technology can really make these structural end-use parts as well. And in this case, it's again replacing a steel material, making this bridge lighter. But something that I did not mention yet, but the materials that this technology works with are what they call thermoplastics. So they're plastics, but they are plastics that you can remelt. So you can reuse those materials. And in this case, that's also a very important aspect for this bridge design, as the routing, or the let's say the city maps, they change a lot. So often these bridges need to be relocated, and then it's very efficient if you can recycle them into new bridges. So that was actually my presentation, highlighting a little bit about what large-scale 3D printing is about, also what kind of size we're talking about, what kind of applications, and how the machines look like. And this is a takeout of some of the customers that we have. I hope this was interesting for you, and I was happy to present this to you.
Thank you, Mr. Jensen. Thank you very much. We particularly appreciate your presentation, because you and your company are based in the Netherlands, and the Netherlands, despite the relatively small population, has a leading role worldwide in additive manufacturing. And there are many Dutch companies that are leading companies in the areas of materials for 3D printing, 3D printers, R&D. So the Netherlands is really advanced in this field. Let me check for questions. I have a question for you. You touched on some applications, the customers, the recyclability. I know the Netherlands is very keen on environmental protection. Some of your applications are long-term applications, like the bridge or some parts for the ship. Do you have a data on long-term properties of your plastic materials? How do you handle the durability of your parts?
That's a very good question indeed. And what makes it difficult is because you use a different process for the materials, that you have to re-evaluate some of those data. But I think one benefit of this technology is that it uses the same materials as that are already being used in other traditional methods, such as injection molding. So there is already a lot of data available on those materials and how they perform. So there are some materials, for example, the material that's being used for the bridge is currently bridges are built or certified against 100 years of usage. And at the moment, we're not sure if this material will last for 100 years, but we know that it will at least last for 50 years. So it's already a decent amount, but there's still some research to be done, and also some applications to be served to see if it works out well. For the molds and tooling, it's a little bit easier to do that, because in that case we talk about cycles. So there we discuss together with the customer how many products they want to make in the mold or using the tool, and then we can actually test it out in a sort of speed up process. So for example, then we test it out to at least make 400 pieces of it on the mold or tool. But durability is of course a very, very important aspect. Yeah.
Okay, well, thank you very much. We appreciate your perspective, and I want to say, I like to tell the audience that for those who do not know, the technology that Mr. Jensen showed is still not popular, because his company combines additive manufacturing plus basically machining plus CNC, right?
Yeah.
So most of the times you buy a printer and it can only print, but in the case of his company, you can print a machine at let's say at the same time, but so you can have the best of both worlds, right? You can have a top you can have intricate shapes built in one run by printing your part, and then you can achieve the surface finish, right, that you cannot with 3D printing, but you can with CNC and basically computer control milling, right?
Yeah, you're completely right. I'm not sure if you can still see my screen or that you see my camera at the moment. But I have maybe I stop.
We can see your camera. We see.
Yeah.
Okay, perfect. So this is, for example, a small element that was taken from a print, and you can actually see that there are a lot of very distinctive layers stacked on top of each other. And for some parts, you really need this to be smooth, of course, and it also needs to look nice, but it also needs to have high tolerances. And that therefore it's really important to combine 3D printing and CNC machining. So you actually use a drill bit to take away this material only for a few millimeters, or and in that case you really make it completely smooth, and that's very important, of course, for the different applications. Yeah.
All right, thank you very much. I'm switching now to the next topic, and which is covered by two speakers. So we have Dr. Robert. So we also switch now area of application of additive manufacturing. So we're moving from industrial applications to health sciences applications, basically medicine related applications. And so we have two speakers today covering this topic, or at least scratching the surface, giving us telling us about some aspects of this type of application of additive manufacturing. So we will have Martina Rama. She's a medical student at Sidney Kimmel Medical College at Thomas Jefferson University in Philadelphia. She's from Italy, and she graduated in 2019 with a Bachelor of Science in Molecular Cell and Developmental Biology from the University of California, Los Angeles. She has a background in basic science research and studied cancer therapeutics at the University of California in San Francisco. She has passion for research and medical advancement and 3D printing. The other speaker is Dr. Robert Pugliese. Is the director of the innovation design at Thomas Jefferson University and Jefferson Health, where he co-founded the Health Design Lab, where he merges design and innovation in healthcare. He has a doctorate in pharmacy and has spent over 10 years of practicing and teaching in emergency medicine. Among his honors and accolades, he has presented at the national venues such as Stanford Medicine X, and in 2019 he was selected by the Philadelphia Business Journal among the top 40 under 40 years old. Ms. Rama and Dr. Pugliese, you have the floor.
All right, can you hear me okay?
Yep.
Good. Well, thank you so much, Antonio. Grazie mille for everybody who is joining in today. We're doing something a little different. We wanted to be, everybody's, I think, really tired of Zoom, so we wanted to be able to have a little more of an interactive experience with you today. So we're going to be giving you a tour of my lab here, the Health Design Lab at Thomas Jefferson University and Jefferson Health in Philadelphia. Antonio already gave a really, really generous introduction of me, so I won't belabor the point. But I want to talk a little bit about what we do here in the Health Design Lab. So the Health Design Lab really is a creative space within our organization where, whether you're a student, a clinician, a professional, or even you're part of the industry, somebody from another outside organization, you can come here and kind of flex your creative muscles, right? We try to bring creativity into healthcare, and we operate at this intersection between the worlds of healthcare and design. And the way we do that is by applying a methodology that we call, a lot of people in the industry have heard this term before, design thinking, right? That is a term for the process in which a designer might use to create a product, service, or space that is not only functional, but beautiful. And for anybody who, it might be a little bit different in Italy if you're based out of Italy, but here in the United States, frequently our healthcare system is neither functional nor beautiful. So our lab really exists to experiment within that space. And how can we make our services in healthcare not just functional and sustainable, right? Kind of both from a cost and an effectiveness standpoint, but also delightful. How can we make that experience a positive one? And we do that in a number of ways. Obviously, today, I'm going to be talking about 3D printing. And when we talk about 3D printing in healthcare, we utilize it in a number of ways, whether we're talking about the improvement of surgery using 3D planning, or whether you're talking about the development of medical devices, or the education of doctors, current and future doctors. There are so many opportunities to utilize 3D printing in healthcare. But that's not all we do, because if you're talking about design, you find yourself touching all of these areas, right? You find yourself, one of the core tenets of design is empathy, right? It is understanding the needs of your user. And if we understand the needs of our user in healthcare, you very quickly leave the hospital, right? Because people come to the hospital because of, you know, what the environment that they come from, right? The way that they grew up, their DNA, but also their zip code, right? Where they live has a lot to do with how healthy you are. So a lot of our work really transcends the actual hospital walls. And we are actively out in the community doing a number of projects. So we do everything from running our design thinking program at our medical school. We also have a product development program and an incubator program here. And then we also do a lot of work in the community. So with COVID, and I'll talk a little bit more about this later, we're operating COVID testing sites and community vaccination sites, again, leveraging that design thinking process to make sure that our services are more effective and more pleasurable for people. So I'll just quickly talk about the space in which I am. It may sound a little bit echoey, and the reason for that is that it's a bit of an unusual space. I'm actually in the basement of one of the largest vaults ever created. So vault, yes, a bank vault. The building in which I'm located is right in the heart of our Center City Hospital campus. It also happened to be the first Federal Reserve Bank of Philadelphia. So all of the gold and currency for all of Philadelphia and the surrounding region was once stored here in this gigantic bank vault. And it's one of the largest, vault doors ever made. And when we discovered this space, some people knew it was here, but it was pretty much unused. It was basically a dump. And we repurposed it to create this creative space where people can come together, access technologies, and use them to improve healthcare. And overall, we've been very lucky because one of the things that we teach in design thinking is this concept of creative placemaking, and that the space in which you exist has a lot to do with or has a lot of effect on how you think and the way you go about doing things. So because the space is so weird, it's such a funky, evocative space, when people come down here to try to reimagine how healthcare can be better, they automatically start thinking differently because they see this place, they're like, wow, it's 100-year-old space, amazing, pretty incredible, unique architecture, and it automatically makes your brain start thinking differently. So that's my kind of bit on kind of design and how we apply it in healthcare. So next, I want to jump into the 3D printing part, and I want to hand you over to Martina, because what we're going to do is Martina's going to show you the technologies that we use here in the Health Design Lab, and also demo them a little bit for you so you can see how they work. And then I'll do a more formal presentation to show you some use cases, right? So some cases of exactly how we apply this technology in healthcare. So without any further ado, I'll turn it over to Martina.
Hello, everyone. Thank you very much, Dr. Paisano, and thank you, Robert, for the introduction. So I'll bring you into the workspace that we have where all our 3D printers are located. We have 3 different 3D printers. In this space, there's 2 different models that I'm going to be talking about. So we can start from over here. So the name of these printers is Ultimaker S5. And these 3D printers are, as you can see, they're all running right now. So you have different things happening. But talking about the technology these 3D printers used, it's something that Dr. Paisano very kindly already introduced at the beginning of this talk. So it's called fused filament fabrication, so FFF. And what happens is that these plastic filaments that you see up here are heated to around 200 degrees Celsius. And then you have a nozzle that deposits layer by layer the plastic, and the diameter of the nozzle is usually 0.4 millimeters. And you can think of it working just like a bit of a hot glue gun, where you have this very smart robot that is laying down the layers, and then you have your final build structure in the end. Some of the characteristics of this machine is that it has a large build volume, which simply means that you have quite a lot of space, as you can see, to build bigger objects, especially when we compare it later to the other machine we have. And so not only can you build pretty big objects, and you can also print multiple different parts at the same time. So this machine is very widely used in a lot of different applications, manufacturing, automotive. It's really good for fast prototyping. You can use a lot of different plastics and materials with this machine. One of the very nice features of this Ultimaker S5 is that it has dual extrusion, which means that it has 2 different nozzles. As you can see, like one is the green color, the other one is the white. And the advantage is, as you can see, that, for example, you can print in different colors if you want to highlight a certain anatomic feature of your print, or one of the nozzles can be used and you can use a specific plastic for your supports. So talking about the plastics and the materials that we personally use at the lab, right now what you see printing is polylactic acid, so PLA, and this is the material that we use most often. But there's a variety of other materials that can be used as well. And when we use the second nozzle to print the supports, that's PVA plastic, and the advantage of that is that it can be easily dissolved in water. So that's very useful, for example, if we need to print any bones or facial feature or the skull, because it would be very hard to remove those manually. So we can just put it in water and the supports dissolve, it's quite handy. So as you can see, for example, here we have 2 different colors printed. We're doing veins and arteries of kidneys. So in that way, these printers are really nice because we can really, as I said, highlight different colors, different structures with different colors. And then over here instead, we have a mandible being printed. And in this case, instead of using 2 colors, since we don't really need it, we're using the other nozzle to print the support material, which is going to be our PVA that we then put in water and it will then dissolve, which is quite convenient. But moving on to the other printers over here, these are our Formlabs 3B. As you can see, the machine itself is quite smaller, so that's why I was mentioning the built volume is bigger for the other ones. And these machines use a technology that hasn't been talked about yet, which is called vat photopolymerization. And this specific one is called stereolithography, or you can also see it appointed as SLA. How this works is that you have a pool of liquid resin or material, and then you have a laser pointer that basically goes layer by layer and polymerizes the structure until you have a 3D print created. This is an example of something that's been printed using this technology. As you can see, it's quite different from what the other ones look. This material is clear, see-through plastic. It can also be sterilized, so it has really a lot of applications in medicine. For example, within the dental industry, it's used for making clear aligners and retainers. And in the medical field itself, it's used to make surgical guides that can be used intraoperatively. And the surgeons, can cut certain bones, and so it can really be used in the OR, so in the operating room. So over here you can see we have a model of a mandible for ENT case where there was a tumor resection, and the mandible has been printed out and it's ready to go. So one thing that this technology, as Dr. Paisano was already mentioning, one of the disadvantages of this technology is the fact that you have some steps after the printing where the model is not ready yet as it is, but you have to do certain things to it after that you do not have to do with the other machine I just showed you. So the 2 steps we're going to be doing, and Rob is going to be demonstrating, are going to be the washing. So right after it's printed, it's going to go into this alcohol solution to wash out any residual material that is attached to it. And after the washing, we will put it, and you can see it, yes. So as you can see, it's still, very liquidy, so everything is gonna wash out. And you can clearly see here the supports. And worth mentioning is the fact that in this case, since only one material can be printed at a time, the supports cannot be dissolved like the one I showed you on the Ultimakers, but instead has to be manually removed So these machines are not great for very complex anatomy because it's difficult to remove the supports manually. So we're now putting our mandible into the wash. And after the wash is done, we're going to be moving the mandible into our curing machine, which is basically a drying step where we're going to have heat and UV light to dry out the structure. And at the end of this process, it will be ready. So again, these machines we use for everything that is used clinically. All these mandibles that go into the OR and that are used for surgical operations are done using these machines. But now we can just go quickly over to our area where we have the hoods and the biolab. And I just wanted to show you the last couple of machines we have. So these are our bioprinters. They're called Alivi 2.0. And I'm actually going to be moving towards the end. So these machines are bioprinters, as I said, and the technology they utilize is very similar to the FFF, where basically you have a printer putting down matrix layer by layer by layer, building your structure. And they basically release this gel-like matrix component, and you can either put your cells inside the gel and then lay it down, or you can create the structure and then later seed your cells. And these are used for bio research from other labs and collaborators at Jefferson. So yes, you can see the nozzle, so very similar structure to the old-time makers that we have in the other room. And this concludes our tour of the 3D printers we have here at the lab. It was my pleasure to drive you through and show you around in the lab. I'm now going to pass it over to Dr. Pugliese, who's going to share with you a PowerPoint presentation and finish up our part. Thank you very much.
Thank you so much, Martina. All right, so I hope you enjoyed that kind of close look at kind of how the technology works. It's surprising how many folks have never seen a 3D printer in action. And I think, you know, again, going back to our design thinking strategy and our methodology, you can't imagine what the possibilities are if you don't understand the tools at your disposal, right? So one of the things that we love to do is simply just to show folks how this technology works so that they can begin to imagine how they could apply it to the work that they do. And a lot of the work that we've done in medicine has been doing exactly that, right? Taking experts, whether you're a surgeon or another type of medical professional, and showing you this is what the technology can do. You know, what would you do if you had some access to something like this? So I'm going to share my screen and bring up a presentation so that I can talk a little bit more about you know, really about what do we do with these machines, right? We talked about how they work, but what are the applications that we actually use, you know, on a day-to-day basis here in the lab? So, you know, we already talked about the vault. Here's kind of like a better picture of the vault door that you might not have seen. It's a pretty cool space. Anybody who's in Philadelphia, I welcome you to come visit anytime. Reach out and I'd be happy to give you a tour. And I talked about kind of the different areas in which we operate right within the health design lab, doing, you know, everything from medical device development to education, community health outreach. But again, we are the home of Jefferson's central clinical 3D printing and bioprinting resource. Now, I do want to mention kind of, you know, the pandemic obviously has changed the world, and it's changed much of how all of us work on a day-to-day basis, and we were no different. And we applied, here we are, this is just last week, me showing the mayor of Philadelphia, Jim Kenney, our mobile health units, because again, we're always thinking about what can we be doing differently. And currently in COVID world, bringing vaccines into the community is, you know, kind of the thing that everybody needs, and that's what we've been working on. And regarding 3D printing, of course, you know, nothing has escaped COVID. And luckily, because we had all of this expertise in the health design lab, we found ourselves being asked to do something very interesting mid last year. And that was when the health system was running out of COVID test swabs. So the long swabs that you insert into somebody's nose to kind of get a sample to test for COVID, the supply chains were breaking down, internationally, and many places found themselves having to figure it out. So we worked with an organization, a number of organizations, but this to use this design that was developed at the University of South Florida, and we actually 3D printed 35,000 COVID test swabs for use here at our organization when we could not buy a traditional test swab on the market. And it was pretty amazing. We were able to spin up, kind of a manufacturing line here. That's me sorting through swab by swab, doing the quality control. And we actually collaborated to publish a major article in with the Infectious Disease Society of America on our test that's showing that our 3D printed swabs were as good as the commercial swabs. So, so we started doing this work about almost 5 years ago. And the Health Design Lab has developed 3D printing protocols for over 10 different clinical departments within the health system. And we do everything from image segmentation, so that's taking the medical imaging, to design and then printing, all happen here. And the lab is comprised of a lot of different professionals, but we do a lot with our medical students and other students within the organization. We find that, kind of teaching and learning is a big part of building up this industry. And we do a lot to kind of make sure that we are training kind of the next generation of physicians to be comfortable with these technologies. Now, I can't, because we're doing a webinar, I can't, open the floor and ask everybody for their opinion. But I find this to be a really great way to teach, why do we 3D print patients' anatomy? And I'll just ask you real quick to look at this medical imaging set and try to figure out what this is. I know you're not all radiologists, but what structure would you guess this is? Just think about it for a second. I'll give you another second. Is it intestines? Is it a kidney? What do you think? Well, I'm curious if anybody guessed a bunch of bananas. Maybe there's some really great kind of minds out there who are able to do that translation between the 2D image and the 3D image. But this right here is exactly why we utilize 3D printing in healthcare, because I've asked rooms full of radiologists what these are and stumped them. But everybody is familiar with what a banana is. So the question is, how can you expect a patient, right, when you're trying to explain to a patient a procedure they're about to undergo, or a non-radiologist healthcare professional, how can you expect them to look at this and begin to understand what we're talking about, right? And the way the way I like to explain this, imagine trying to explain to somebody for the first time how to peel a banana using just this black and white grainy image of a slice by slice of a banana, right? It's incredibly challenging to do that mental gymnastic to translate that image into what that means in a three-dimensional space. So why not just give somebody a banana? And that's exactly the point of what we do using 3D printing technology in healthcare. So there's a number of spaces in which it's used. There are centers of excellence around the world, incredible work doing from implantable 3D printed technologies to things that are simply just used to help educate patients. So everything from rapid prototyping, which means basically just creating new devices, bioprinting, which I'd be happy to answer questions about at the end. And then, but really what I'm going to be talking about today is kind of the space of personalized medicine, patient communication, and surgical planning. And we work in those three spaces for a number of reasons. One is that there's a lot of low-hanging fruit in this space. I can't tell you how many people have come up to me and said, before I underwent this surgery, I had no idea what to expect. Yes, my doctor had told me, yes, somebody asked me to ask questions, but I didn't even know what questions to ask. So enabling patients to have to be able to ask better questions has everything to do with improving the quality of care and the satisfaction with care. And then you get into the surgical planning and the medical training space. Again, I don't know how many times I've heard extremely experienced clinicians say, why do I need a 3D print to practice my surgery? I've been doing this for decades. I'm really good at it. I don't need it. And then we give them this tool. And suddenly they have a new piece of information they've never had before, right? And I think anybody who's ever tried to fix something with the wrong tool knows that when you have the right tool, it's amazing how easy it is. So even the most experienced, professionals find value in having new information. It's the same thing that happened when CAT scans and MRIs first came out. Everybody said, we have X-rays, why do I need a CAT scan or MRI? But it's more information and it's helpful. So the value of doing this, there's a number of reasons why and how we kind of pay for this work. How does this work sustain itself? A lot of that is in time savings, right? Time savings in the operating room equals cost savings. And then there's also, those are the tangible benefits. Then you have intangible benefits like better patient satisfaction, more surgeon confidence. And the way we do this work here is just a quick overview of the workflow. So, and the thing I'll point out is that we still use just our standard imaging techniques that we would use for any patient coming to our organization, right? So we're not getting an MRI just to 3D print something. We're not getting a CAT scan. This is something that you would already be getting as part of your standard of care. And we're just taking that information that we've already gathered and using it for a new application, right? So we take those CAT scan and MRI images. We then turn that into a 3-dimensional digital file that's called segmentation. Then we then take that digital file and we 3D print it. And throughout the whole process, right, we're collecting data about how we can improve and to make sure that our quality is up. Here's an image of that kind of segmentation workflow. The image on the left is this is, I believe, is a CAT scan that you see kind of scrolling through the slices. Right, that's what it, and then you see that there's colored blobs. So basically it's like coloring. We literally color in the things that we want to be 3-dimensional. And then in the picture in the middle, that is actually the same medical data set that has now been made into a 3-dimensional thing. You can already see, you may not have known that was a hip from the left picture, but now you can probably tell from the middle picture. And then the right picture is the 3D printer specific software that we use to prepare the file for 3D printing. We use a software called Materialize for that. It's incredibly advanced, but it's amazing kind of how easy it is to get into this space. There's actually free open source software out there that if you wanted to learn or experiment with this technology, you can teach yourself with the resources that are online. And I really do see that this is going to be a big industry, and it's already becoming a very large industry of people who understand these technologies and how to utilize them. Now, I just want to give a quick warning. I am going to show some images of surgery throughout the next portion. So if you're a little squeamish with blood or surgery, just be aware that I'm going to be showing some of that. So I'm also going to quicken my pace up because I don't want to go over time, but I do want to run through some of these cases. So here's the first case. So how do we use 3D printing in head and neck surgery? So I showed you a couple mandibles today, right? These jaws that Martina was talking about. And we actually use these in patients with cancer who are about to undergo reconstructive surgery of their jaw to pre-bend the reconstructive plates that are going to be used in that reconstruction. So you can see here somebody has the 3D printed jaw, right, the mandible, and they're actually bending that titanium plate over that, using that as a kind of bending jig so that when they get into the operating room, the standard of care right now is you get into the operating room, you have a straight bar, and you bend it according to what you see on the table with your patient. This enables the surgeon to do this ahead of time, try to get it closer so that you have, you spend less time in the operating room doing that. Now, this is a great video, and let me just see. Here, now you should be able to hear the sound.
It was the only time in my career where I've ever bent it, and I had to make no like adjustments. It was like it went straight through. It's one of those like ridiculous things.
So that's one of the top head and neck surgeons at Jefferson talking about how in his career he's never had a plate go in that quickly, right, for one of his patients. So hearing things like that gets us really excited because again, we found a use case for this technology that really benefits care. Now, not only do we use this for our patients here, but we also found another use case for them using them on our medical mission. So our ENT surgeons every year go to Haiti to do medical mission work. And by utilizing this technology to decrease the time that it takes them to do their work, they can do more cases. So again, a really great use of the technology to increase the amount of cases they're able to do when they're in a low resource environment. Something, again, that I wouldn't have imagined that would have been possible just a few years ago. Now, quickly for the numbers, people out there, I'll talk about cost benefit. One of these models is surprisingly cheap to make, right? So one of those mandible models, even with the time and effort involved, you're talking only about $67 to make one of those things. Now, operating room time in the United States costs between $33 and $100 a minute. Every minute we're in the operating room, we're spending essentially on average 50 bucks. So we pay for this model in a few minutes, which is kind of insane to imagine. But that's, again, how impactful this technology can be and without spending a lot of money. So the next thing I'll move into is in high-risk obstetrics, right? So this is complicated pregnancy and birth. So in complicated pregnancy and birth, the big challenge is that you have many different specialties who have to understand what they need to do to deliver the baby safely. So it's not just the obstetric surgeon, right? But it's also vascular surgeons, other people who with expertise in different areas. And they have to get on the same page. How do they do that? Well, traditionally, they would just look at the medical imaging data. But we found that by, again, 3D printing that model, it is a map for them that everybody can understand. So you can see here, the previous slide, this was that two-dimensional imaging and segmentation. And here it is. This is actually a three-dimensional model of a woman's uterus who has something called leiomyomas or fibroids, which can grow really large in pregnancy. And each of those could be really dangerous if a surgeon was to cut into them because there's a lot of vessels, a lot of blood, could have a lot of blood loss. So we 3D printed that because, again, you're able to very easily understand where are the things that I need to avoid and how do I make my incision so that I can avoid them quickly. And we saw our surgeon actually using it as a map in the operating room. Here she is pointing at a particular fibroid that she wants to avoid while showing her resident kind of what the next step is going to be. I encourage you to, if you want to hear more about specifically how that all goes down, just Google Ultimaker and Jefferson, and you'll find a couple of videos about that case study. Next, I'll go into liver resection, because this is fascinating, not just because it's a really complex surgery, but how we made them. And kind of thinking about the last speaker and how he was combining two different technologies in a really amazing way, this is exactly how we do this type of model. So in these cases, these are patients with cancer of the liver. They have to have a portion of their liver removed. This is what the imaging looks like. And we're able to take that imaging again and make it three-dimensional. However, we do it using two technologies, not just 3D printing, but mold making. We actually create part of the anatomy is 3D printed, but then we actually 3D print a mold of that patient's liver so that we can have this beautiful clear model without having to have a really expensive multi-material 3D printer. We could do it for a lot cheaper. And you can see the two structures here. You have the 3D printed elements. The red is the vessel, white is that gallbladder, green is the tumor, which is sitting right on top of a vein, a venous vessel in the liver. And when it's all done, when we have the 3D printed thing in the poured silicone mold, this is what it comes out as. And it's quite beautiful to show you that you can actually take this and handle it and move it around. And the surgeon can use it to visualize what their surgical approach is going to be, because the goal of this procedure is to spare as much liver as possible. And not only do we use these for, again, that surgical planning, but we use them to help educate the patients on what they're about to undergo, right? Actually showing them, we hope to save this much of your liver. If we can't, this is what we're going to do. If we can, this is what we're going to do. And again, allowing the patient to understand what they're going to undergo so they can be more confident about their decision making. Now, this is kind of graphic, but I just wanted to show you, it's always amazes me. Like, we know the technology mimics what the actual anatomy is on a one-to-one scale, but when you actually see the tumor, this is like the liver that's been resected, you can actually see the tumor in the liver in almost the exact same place of where the tumor was in the model. It's pretty incredible. Now, I'll move quickly on to the next case study. This is called a radical hip reconstructive surgery. So you'll notice that there is a trend in these cases I'm talking about, in that each of them, many of them involve cancer, right? Or a case in which there is a lot of variability from patient to patient. And that's where 3D printing does best, right? 3D printers were not made to make 1,000 of the same part. There are other technologies that can do that better. The 3D printers are really great at printing each thing being entirely unique, right? Essentially, it's sculpting robotically. And because of that, because each patient is unique, that's why it's the perfect technology to use in cases like this, where you have a patient with a very unique pathology that we need to address. So in this case, you can see here, this is a patient with a very large tumor of the hip. The reconstruction of this type of case requires a lot of different specialties, a lot of different expertise. And just looking at this, you can see that it's going to be kind of a large, complex procedure. So what we're able to do, again, with this technology is take that medical imaging data, actually 3D print it so that the surgeons can get their hands on the model and actually practice it. Because again, there's one thing that is true, I think, about most humans, is we really do think in 3D, right? Many of us are not great at taking two-dimensional objects and doing, again, that mental math as to what it means to be three-dimensional. So if you can actually hold that model in your hand at 1-to-1 scale, and Greg, can you grab me actually the hip model, and I'll just show you, because it's pretty amazing to see, like, I'll hold it up to my head and you can see how large this thing is. That does a lot for, kind of, here it is next to me, what that 3D print looks like at scale. It's pretty massive. That does a lot for your understanding, right? Doing that, having that tactile feel and being to manipulate the model. So our surgeon actually practiced the procedure on this, utilizing this model ahead of time in his garage. He took it home and he, hacked the tumor out of it. And in this particular case, they actually reconstruct the hip using portions of the fibula bone, right? So that's a bone from your leg. They take that bone out of the patient's leg, they take pieces of it, and they use that bone, that native patient's bone, to reconstruct the hip. So we actually 3D printed that patient's leg bone, we 3D printed that patient's hip, and the surgeon practiced that procedure ahead of time using this model that, quite frankly, only cost about, this probably with labor was about a $200 model. And this, I love images like this. So on the left, this is the model that the surgeon practiced on in his garage. And on the right is the post-reconstructive surgery imaging. And again, it's just amazing to me seeing that, we are able to, it's just amazing that these technologies are able to enable our surgeons to practice with such high fidelity what the procedure is going to look like, to the point where what actually happened on the patient was almost identical to what he practiced the day before. Now, all of the technological stuff is impressive, right? It's pretty amazing that we could do this. I still find it hard to believe. I was a 3D printing doubter when I started this work, until I discovered that the use cases were really incredible, especially in healthcare. So for me, when I hear, I'm going to play this reel of one of our hip patients, and what he said about how he felt about this, this technology being used in his case.
And I'll go back to the phone call that the doctor gave me the night before. He says, I'm driving home with a model of your pelvis next to me, and that, along with seeing it, just gave me the confidence that, hey, look, this is going to be something that was going to work, because again, they said to me they were not really sure that the screws could work, and that bone was going to be the best way to go, and then this is where it was going to go. I can actually see it and understand it, what they were going to do.
Right. So,
and I'll go back.
I love hearing that video, because that term confidence, right? Imagine you were undergoing this big, scary procedure. It's important to be confident that you're making the right decision about your health. And we're able to at least help a little bit with that, right, using these technologies. So the last thing, this is a case that we just recently did that I'll mention, and I'll ask you to Google this one. It's called the Cortimo trial. This was pretty freaking amazing. We were the first center in the United States to utilize a brain-computer interface on a stroke patient. So this was a guy who had a stroke, lost use of one of his limbs. And this case just happened. You can see 5/18/21. It just went down we have a Center for Neurosurgical Excellence here at Jefferson. And this patient, through the implantation of electrodes in his brain, it was able to now control a robotically assisted prosthetic arm that helps him move his arm, and he's able to do that all essentially just by thinking about it. Pretty far out there stuff. He's the first patient in the world to have this done, first stroke patient in the world to have this done. And again, in a very simple way, we were able to 3D print that patient's brain, his exact that brain. And it was easier than you would think because we had the MRI data. And using that, the surgeons were able to practice over and over and over again. And here it is. This is in a different color because we did it in a few different colors. The surgeons were able to practice, exactly where they were going to place those electrodes. And here's the two different sides. I always actually find it kind of amazing how small brains are. Once you get in, this is a 1-to-1 brain size. I guess it fits pretty well here. And again, the detail that we're able to get with these machines, these relatively inexpensive machines, is in a sub-millimeter accuracy, which means that we feel confident that we can use this as a training tool for something as delicate as neurosurgery. And here he is post-procedure. It was an overall success. He was very quickly, it's amazing how quickly he was able to control the arm using this brain-computer interface. We had such a small component, I can't stress enough, kind of the amount of work and experience that went into it from the neurosurgical team and the technological team. We were just proud to be able to have a small part in enabling them to do it just a little bit better and be a little bit more confident about the procedure. And I won't go too much into bioprinting. We could have a whole hour-long discussion on bioprinting in that space, and it's growing and it's exploding in the world right now. But the last thing I'll leave you with is that 6 years ago, this technology was completely different, and it's still changing rapidly to the point where when somebody comes to me and they say, "Can we 3D print this?" I don't have to stop and even think about that. The answer is yes. We pretty much anything in any color and any softness and any material can be 3D printed these days if you have enough money and access to technologies. The question is why, right? And that's the question I continually ask people is, what can we do to improve that experience? What can we do to improve the design of this process? Who is the end user? And frequently 3D printing may have a component in it. Sometimes it doesn't, but it's amazing to know that that technology is out there to be able to, enable us to do amazing things. So thank you so much for listening. And I think I did okay on time, and I'll turn it over back to Antonio. Grazie.
Thank you, Dr. Pugliese. Thank you, Ms. Rama. Thank you very much. It was really a treat. It was a very extremely interesting, informative, and entertaining and clear presentation. I like to stress to the audience that what you are doing is, well, it would be, I felt, almost at the edge of science fiction. So your applications are cutting edge, and they are there are very few like yours currently being investigated, and utilized. We also appreciate very much the tour of your lab. Let me see. Let me see. Well, so I mean, one question. I'll just limit ourselves to one question to give the next speaker some enough time. Let's say, do you know about these applications or similar applications as yours? How spread are in US, and where are they working on similar applications like yours in US?
Yeah, I mean, we're at this phase where there are a lot of kind of groups who are sort of dabbling, right? Who are just kind of starting to explore this space. Maybe they've bought a couple 3D printers, but they don't have a dedicated team. And that's on one side of the spectrum. And then you have places like centers of excellence. Like if you're interested in 3D printing in healthcare, I really do encourage you to look up the work being done by the Mayo Clinic. They are probably one of the most advanced medical 3D, hospital-based. I got to stress that too, right? There's a lot of medical-based 3D printing happening out there in industry. But what I was talking about specifically are hospital-based 3D printing, right? Like my work, I work for the hospital. This work is happening at the hospital. Mayo Clinic really is leading the way in hospital-based 3D printing. They do incredible work with a lot of different technologies. So what you're seeing is a few centers of excellence around the country. You know, usually they're at academic medical centers and things like that. But you see it used so widely at all these different places where it's even hard to track. And one of the first places where 3D printing was used in healthcare was in dentistry, right? So you see a lot of dentistry practices utilizing 3D printing because actually a lot of 3D printing technology was developed originally for dentists. And we've all used them in other industries for different things. So that's another place where you see a lot of it being used. But I think in the coming years, you're going to begin to see this as being the standard of care in a lot of surgical procedures. And we're getting to the point now where insurance providers are going to start reimbursing for this as well.
Okay, thank you very much. Appreciate it. And we now move to the final speaker. And I'll try to be as fast as possible to introduce him. But I want to say that now also we are switching aspect of additive. We're switching aspect of additive manufacturing, and we're moving to an area of additive manufacturing that has become more important as additive manufacturing gathers more business. And the area is intellectual protection. So we have seen so far great applications and of great processes, technologies related to additive manufacturing. But what happens when you have a new idea for a new process or a new material for additive manufacturing? How do you protect it? And this is where Mr. Belisario comes in. So he's the next speaker, and Martin Belisario, he focuses his law practice on intellectual property and technology law, including technology licensing, trademarks, copyrights, counseling, and litigation, and representation before the United States Patent and Trademark Office and foreign patent offices. His patent practice focuses primarily on the mechanical arts. Since 2005, Mr. Belisario has been selected as a leader in the field of intellectual property and has consistently been named one of the best lawyers of America in the area of intellectual property. Mr. Belisario was also named the Best Lawyers 2020 Lawyer of the Year in the Philadelphia area. And he has been recognized as a Pennsylvania super lawyer, quote unquote, by Thomson Reuters. And he's also one of only 6 patent prosecution attorneys recommended in Pennsylvania. Mr. Belisario, please go ahead.
Thank you, Antonio. That was very kind of you. That Robert and Lucas, fascinating stuff you guys are doing. I enjoyed every second watching that. My mind was popping the whole time with how you could protect all this stuff. And so I'm going to do just basically a little, I'm going to call Patent 101. And I'm just going to walk through the basics of what do you need to do to get a patent, and then we'll talk a little bit about infringement and some of the more sidelight IP areas, trademarks and copyrights, because they can get involved in the additive printing area. So let me share my screen here. All right.
That looks good.
We good?
Yep.
All right. So what is IP? It's an intangible product. It's something up here inside of your head. The kind of stuff that Robert was talking about, being imaginative in the 3D printing area. They put their heads together. It's the creative output of your mind that provides you with a competitive advantage. And it can be protected. There's broad range of possibilities. It can be circuitry, it could be mechanical structure, product designs, methods of manufacturing, compositions, combinations of things. It's all over the place. And lots of the things that Robert and Lucas were talking about are certainly protectable. So let's talk about a patent. What is a patent? Well, it's a contract between the inventor and the government. It could be European government, it could be US government, but that contract says, in exchange for giving us all of the details on how you make and use the invention, if it's patentable, we will give you the exclusive right to prevent others from making and using that invention for a period of 20 years. But the idea is that you have to have a complete description of the invention so that when the patent expires, it goes into the public domain and anybody can make it. So there's 3 types of patents: utility patents, design patents, and plant patents. I'm only going to talk about utility and design patents. So utility patents relate to a process, machine, manufacture, accomplishment of matter, or any new or useful improvement thereof. It covers just about everything. The things that you can't protect are the laws of nature. Software has become much more difficult to protect, especially if it's in the finance or algorithm area. How long does it last? 20 years from your initial filing date. Now, it can be extended. If the patent office delays in examining your application, they will add more time onto the end of your monopoly. So there's 4 requirements to get a patent. 1, it has to be novel. 2, it has to be useful. 3, it has to be non-obvious. And 4, you have to give a full disclosure. So let's walk through those real briefly. So what's novelty? Novelty means it cannot have been publicly disclosed or placed on sale or described in a printed publication more than a year before you filed the application. So what does that mean exactly? That means if somebody has done something identical to what you've done more than a year before you filed, you're out of luck. You're not going to be able to get anything. But this grace period of 1 year is unique to the United States. There's no grace period in most foreign countries, including Europe. You have to be on file before you do anything. So if you put your invention on sale or put it on a website, in the US, you got until 1 year from when you first did that to file. Everywhere else, you need to file before you do any kind of public activity. All right, usefulness. This one's a piece of cake. Just about everything is useful. I'm going to give you some samples of patents that I'm just going to roll through them of some things that are useful, and some of them are pretty silly, but they're still useful. So everybody knows this. I'm sure they played the game, but it goes back to 1935, the game Monopoly, and it was patented way back when. It is now expired, but they have protection through the name Monopoly and all the pictures of everything that they can protect elsewhere. Here we go back to 1893. I'm reading that right? Yeah, 1893. The invention of the zipper for a shoe goes way back. Here's a method of folding a beach blanket. I don't write these patents. I just show them to you guys. Now, for those of you who like to walk in the rain with your glasses on, you could also get some windshield wipers for your glasses. My favorite for my folks in Italy, for the lazy pasta eaters, an easy spinning pasta fork. You just push down and it spins and puts your pasta on your fork. All useful. Thumb wrestling, a ring for a thumb wrestling, useful, but not terribly commercial. Those of us in the US who played in high school, played football, the paper triangle football at lunch, that game can be patented too. And really silly stuff. If you're lazy about taking your stockings off, you can have a machine for take your stockings off. All these things are crazy, but they're still useful. And that's all you require. So here's the hardest part of getting a patent. When an examiner looks at an application, he looks first to see, hasn't been done before. Is it novel? And then he starts looking at things that are close. And he can then decide if it's close, well, one of ordinary skill in this industry would find it obvious to make the modification so it'd be the same. And that's the area of patent law that is the most bitterly fought. I mean, patent attorneys get paid the big dollars, so they argue this point, what's obvious and what's not. And it's really a examiner's burden to objectively establish that it's obvious. So he's got to come back and find some good, what we call prior art or prior devices, and combine them in a way that one of ordinary skill in the art would do. And there's reasons not to do that sometimes, and that's what we argue with the patent office. All right, I've talked about utility patents. Now design patents. Now design patents, they cover the ornamental appearance of an article. So it could be anything like the Coca-Cola bottle could be design patented. A speaker right here could be design patented. Anything that you can make physically, you can protect with a design patent, but it only protects the ornamental appearance, not how it functions, it's how it looks. Design patents don't get published. They ask for 15 years from issuance, and they're the same requirements as utility patents. You have to be novel, you have to be useful, you have to be unobvious, and to have a full disclosure. And the patent office in the US will examine them to see if they've been done before. In a lot of countries, they don't. In Europe, with the European Community Design, they automatically just issue them, and there's no examination. And if you go to assert it, they'll fight over whether it's valid or not during the assertion process. But the big thing about design patents is they're really narrow. You're really limited to what you see. They're great for knockoffs from China. And that's the purpose of them, is like, does it look the same? Would it confuse somebody buying the accused product thinking it's the patented product? It's a very nebulous standard. So let's talk about 3D printing and patents. All right. So what are the things that you can protect in the 3D printing world with patents? Well, those robots that we all saw, those fancy robots picking up printing heads, moving them around, they're the printers themselves. Anything you do to improve those, that make them better at 3D printing, are going to be protectable. The materials, we have those, all the plastics and other materials that are used to print these devices or print these products. If you come up with a better material that's faster to print, dries faster, enables speed to be used to make these products, certainly protectable. And the methods of producing the products, how you go about producing the product with a 3D printer, can also be protected. Like, I love the description of the support material in some of the examples that were given at the lab, and they showed the being dipped in the bath to get the support material out. I mean, if you were the first one to come up with a support material in 3D printing, that's probably patentable, and you could have patented that. And of course, the products produce themselves. Whatever you produce with the 3D printer, you can protect with a design patent, and you can protect with the utility patent, as long as you meet these 4 requirements. And so the short answer is 3D printing is wide open in terms of IP. You can protect anything you can in terms of the printer, the material, the products produced, and how you do it, as long as you meet those 4 requirements. You could even protect the software that controls the robot, if it's something special about that. And those surgical methods that Robert was talking about, protectable. All this stuff and how you use them, the 3D models to do a surgery, that's protectable as long as you meet those 4 requirements: new, non-obvious, useful, full disclosure. You do that, you're in great shape. And by the way, this is a design patent. I'm sure many of you know this who have kids. That is the Super Soaker. The Super Soaker was invented by a gentleman named Lonnie Johnson, and he invented it in his garage in North Carolina. And it didn't look anything like this. That's why he's not the inventor of the Super Soaker for the design patent, because his product was a prototype and didn't look anything like this. But when in the mass production, they came up with how it should look, and they protected the look of the Super Soaker. But Lonnie Johnson ended up in the Inventor Hall of Fame at the Patent Office for inventing the Super Soaker. It's fascinating stuff. All right, here's where you can get in trouble. Now, I've talked so far about what you can do to get a patent and what the requirements are very broadly. But the other side of the coin is, how do you avoid others' patents? Because if your printer or your materials for printing or the product you're producing with the printer infringe an existing patent, that's patent infringement. And the patent owner can prevent you from making, using, and selling that product, that printer, et cetera. So you want to come out with a new product, you just put it on the market and take your chances. People take different approaches to it. Some people have the stick my head in the sand approach, and I'm just going to put it on the market and I'll take my chances. Somebody's going to sue me. It's risky. Others will conduct what's called a freedom to operate search. That if you're going to print something with a printer or develop a printer and you want to put it on the market, you want to make sure that you're not going to step on somebody else's toes. So we do a search of previously issued patents that are still subsisting to determine if the product you're going to make is going to be a problem. So there's a couple of things there. You might come across something that's a problem, but if you make some design changes, it's easy to get around. And the biggest thing is that if you do make something that is infringing a patent, you're looking at lots of damages and very expensive litigation and paying royalties. And some of the things you can avoid is if you find a patent early on that's an issue, you can go contact the patent owner and say, gee, can I get a license? So it's proactive in terms of avoiding problems down the road. Trademarks, this is a little more esoteric. If you're printing products that have trademarks on them, you could run into problems with trademark infringement with your 3D printer, very basic stuff. Now, copyrights. Now, this one scares me because the difference between patents and copyrights is that you could make something with a patent. You could be in California and create something on your own and never seen a patented product, but not realize that somebody in Philadelphia had patented that invention. And because even though you never saw it, copied it, you invented it yourself, you can still be involved, you still be charged with patent infringement, even though you didn't copy anything. The flip side of it is copyrights. Copyrights say, if you've seen it and copied it and produced it, that's a copyright violation. So you've copied it. So patents protect the products regardless whether somebody copied it or not. But a copyright only protects against people that actually copy what they saw. So if you see a product on the market and you like it and you want to then copy it with your 3D printing machine and say it's a sculpture of some sort and protectable by copyright, you're running the copyright problem. So you have to be careful that when you create products in 3D with 3D printers, you're not creating things that are already on the market that could be protectable by copyright. And that's a tougher area. The safest thing to do is don't copy things. Make your own products. Don't look at other things and use those as the basis for your work. I finished early, Antonio. Questions, anybody?
Yeah, so well, first let me thank you. Let me thank you very much for your presentation. I have to tell the audience that very accomplished patent lawyers like Mr. Belisario can be very expensive. So today we are very fortunate because we received his advice for free. So yes, but the question is, I have a quick question because yeah, we're running out of time. Do you do the 15 years apply to any type of patent in US or it depends? The 15-year protection time.
All right, so utility patents is 20 years from the filing date, and it's for all patents. Okay, all the utility patents are 20 years. They can go a little longer if there was delays at the patent office, or some drug-related patents can be extended because they were held up in federal regulatory review. So they can often add time on for that reason. But they're all 20 years except for design patents, which are at 15 years.
Okay.
From issuance.
Okay, well, thank you very much. I have to run because we are running out of time. And so before I conclude this event, I like to acknowledge again the speakers for sharing their valuable time and expertise. The Italian Consulate and Philitalia International, and Hyper Design, the company that has done an outstanding job in ensuring a smooth broadcast and handling computer and social media related matters. Many thanks to you, the audience, for watching. You will find the recorded version of this event on YouTube in a few days. Please type the keywords Philitalia Symposium. Saluto e ringrazio coloro che ci hanno seguito dall'Italia e gli ricordo che tra pochi giorni sarà possibile trovare la registrazione di questo evento su YouTube usando come parole chiave Filitalia e Symposium con la lettera Y dopo la S iniziale. And last, after you leave this broadcast, a prompt for a short survey will open up by itself. Again, thank you very much, especially, well, thank you very much, the speakers, the audience, and have a good day. Bye.
Bye.
Ciao.
Ciao.
Ciao, ciao.
Thank you. Thank you, everybody.